All right, I'm happy to introduce our next speaker, Everett Vazana. He is the Manager of Digitalization at North American Stainless, a division of Acerinox, a global leader in stainless steel production. North American Stainless instituted the Digitalization Department in 2018 and has been working on advanced analytics and Industry 4.0 integration for several years. Prior to digitalization, Everett was the electrical engineering and maintenance manager at the Ghent, Kentucky facility for over 20 years. And throughout this time, they expanded into a fully integrated stainless steel production facility, including melting, hot and cold rolling, and finishing facilities. Welcome, Everett, to the stage.
Thank you. Forward, backwards, yep. Light. Okay. Okay, great. Can you all hear me? Mic check. Okay. All right. Fantastic presentation so far. Really hits home with a lot of the things that I'll probably talk about today. But I'll start out with a quick story, a fun story, I hope. It was 1982. I went to an exhibit with my dad. I was still young, 82, at Buell Science Center in Pittsburgh, my hometown. And it was called Real Live Robots. Real live robots. But in reality, okay, it was a lot of R2D2, canned robots looking things. But there was one really interesting thing. It was a pogo stick robot. And I think you guys have one here. And I would love to see it before I leave MIT. Because it was my memory was jogged listening to a Lex podcast about it. He was talking about it with Boston Dynamics. And very impressive. It was tethered, so there was some controlling going on, some supervised controlling going on from, I think it was a CMU grad student. But in any case, seeing that really inspired me to follow this path in career. Unfortunately, I didn't go into robotics, electrical engineering, manufacturing, but lo and behold, it all comes back around because now we're looking at instituting all these AI, machine learning techniques within the manufacturing of stainless steel. So it's been a great journey, and I'm happy to share some of my experience with you on it. I'm going to talk about a little bit about our infrastructure, 2 deep dives into use cases, and some conclusions. This slide, I'm just going to wing it on this one. I really want to talk about 3 different challenges within manufacturing. First one, we all know data. First one's data, and we've talked about that. We've heard about that all morning. And these are all lessons learned by me because getting into this after working in the plant for over 20 years, putting in PLC systems, putting in data historians, everything like that, I thought we've got plenty of data. This will be an easy win, machine learning. But that is not the case because you may not have the granularity, it may not be clean data, and you certainly may not have all the data. So data it's never going to stop, data engineering side of within manufacturing. The second big challenge I have is horizontal application of use cases. Even if I have 2 lines exactly the same, 2 slitter lines, 2 Zenzmer mills, different years, different manufacturers, different OEM, I can't take a specific tuned model from one and translate it to the next. It's very difficult to do that. So you don't see the ROI right away with a lot of use cases that you spend a lot of time developing. And hopefully, they're useful to some point, but then it's hard to horizontally translate. And I think that's the case for a lot of industries, but maybe some language, vision systems, you can translate a little easier. The third thing I'm going to talk about is expectations, managing expectations. So this is a 2-edged sword. I heard it earlier that you have to have the CEO, above the CEO, BOD, everyone involved in AI, which is true. But the expectations are what we see every day when we pick up our phone, when we order, when we go on Netflix. Everyone knows that AI is a part of their lives. So why isn't it running the machines yet? So you have to manage these expectations, and it's very difficult to translate that. This next slide is another general introductory thing, data landscape, which is another lesson learned. Really, you need an extremely diverse team to make a good progress on your use cases and implementations. So we focus a lot on this slide, the machine learning. You see down there in green, it talks about what algorithms. Are you going to use neural network, how many hidden layers, all that kind of stuff. But that doesn't matter if you can't sell it, if you can't visualize the results, if you can't explain how it's going to save money, how it's going to make an ROI for your CEO. So if you look around the outside of this, the soft skills, visualization for sure. You can look at 1 million histograms and violin plots and anything you want, but people don't necessarily understand them the first time you look at them. So you have to well label it, right? And then you have to have your subject matter experts, your SMEs. If you're not the SME, you have to find one to give you the first principles approach to your data engineering. And it's not listed here, but I want to mention it now, is the case of ethics. Again, a big surprise for me in the last 5 years, and especially in a steel plant, because it's not language modeling, it's not vision system, it's data. But surprisingly enough, there's plenty of ethical discussions that come up when we look at data, because data is power, and data can be skewed. As simple as the y-axis, auto scaling on a y-axis. That can make everything look crazy. But I'll give you a specific example on this. It's something we've looked at, is safety systems, vision safety systems. So you can currently implement a system using your cameras in the plant to determine if people have the correct PPE on, or if they blew a stop sign, or if they're driving too fast, which is great on the outset. It's like, oh, this is great. We're going to solve a lot of problems. We're going to have better leading indicators. We're going to do good. But how you adopt that can change the culture of your plant, and it could have negative impacts. So something to keep in mind, all these skills when you're getting into this field. It's a crazy field. It's a roller coaster ride. I miss just doing electrical engineering sometimes, because a 2-week sprint, you think, I'm going to solve the world, and then 2 weeks later, your next sprint, you're back to square one. So, okay, I'm going to switch around. I'm just going to give you some background, where I'm from, a little bit about the plant that's going to help you understand the use cases, I hope. NAS has been established since 1990. We're part of Acerinox. We have manufacturing plants like this in Spain, South Africa, Malaysia. This is the plant I work at. It's an hour south of Cincinnati on the Ohio River. We use the river for raw materials and also for water. You can see we're fully integrated. Our melt shop's on the right, and the kind of process flows to shipping on the left side of the picture. This is from our website. I encourage you to look at it. We also have a video from how it's made several years ago, explaining our plant in more detail. But just real quick run through of this. We get scrap material in, mostly scrap stainless, austenitic or ferritic. We melt it in the electric arc furnaces. We have 2. Further processing through the melt shop, make a billet or a slab. The slab goes through hot rolling process to make plates or coils. The coils then go through our cold mill, where it's reheated, cleaned with acid tanks. It goes through a Zenzimer mill, which is this funny-looking 20-roll cold rolling mill. And then after all that, it goes through some final processing, cutting into pieces, and I'll show you some of our final products to give you a context. So we don't necessarily make a final user product. This is the stainless that goes into refrigerators, beer kegs, mufflers, anything you might touch in North America. You see coils, blanks, sheets, and also we have a long products facility, which makes the rebar, angle, and wire. Okay, now I'm going to zoom in. We have 1,400 employees. My department doing digitalization, machine learning, all that, 6 people. So we're a little stressed out, but we have a lot of power users out within maintenance, engineering, and with the operations department. Our basic goal is to use data to assist in any of the main KPIs or OEEs. This is the Industry 4.0 that we saw earlier. The ones I have boxed are what I'm going to talk about our specific use cases. Big data is traditional machine learning that I'm going to talk about, and then on the other side is called cloud computing. So we're leveraging some of third-party software to do some cloud use cases. But we have a little bit in every area within our plant. 3D printing, AGV systems, a little bit of everything. Cybersecurity, very important in the last couple of years. This is our tech stack. I'm not going to dwell on this. It should be familiar, I guess, but we use R and Python and Jupyter Lab to do a lot of the data science. On the very far side of the drawing here, we've got two main data sources. We've got our time base in our data historian, which is about 1 second for most of our variables. up to 100 milliseconds, over 30,000 signals from the machines. We do have siloed high-speed EBA systems. But outside of that, outside of the real time, we've got contextualized data within SQL databases with our MES. So that means I can go to coil number 1, 2, 3, see when it ran, get the genealogy, the history of that coil, the coil twin, if you will. So we use this data stack. Everything else is pretty normal. And we do, on the right side, some of our UIs are listed, as well as third party. These are some home-built dashboards that we have developed in-house in the last couple of years. A lot of it is not overly complicated, but it's data visualization back to that, just to kind of push users into the data science side of things. So you'll see a lot of histograms, Sankey diagrams, flow charts, that kind of thing that we have a website set up. And one of our first projects was this smart alarm system. So that takes data from real time and also contextualized. So I can say on the hot mill, if I'm running austenitic steel, I want this temperature to be within this range. So this is just kind of an advanced way of setting up alarms. And that system can send alerts to me on SMS or emails or anyone in the plant that subscribes to it. And I did mention before, we only have 6 people, data science people working, but we have over 70 people that are actively using SQL and notebooks. So we have a good population of mainly younger engineers, material science, electrical, mechanical, that understand the power of data science in their everyday life, and they're trying to make their jobs easier, obviously. Okay, so we'll jump into one of our use cases. The first one was actually done as a partnership with McKinsey several years ago, and McKinsey was here earlier, hit a lot of bullet points that were pretty much spot on as far as implementation of machine learning. This is going to be a traditional use case, XGBoost model, and it was for, if you remember, the first step was get raw material, put in an electric arc furnace, and melt it. That's what this is trying to optimize, is that process. And the target for this process is the final temperature when you pour out the liquid steel. The features, I can't list all the features, but we'll take a look at the shaft plot in a minute. But basically, we just took 2 years of all the historical data. A lot of it was contextualized, not necessarily real-time data, but contextualized data about what we ran and what it took to get to what we ran. And then, of course, looking at the targets. Once we build a model, traditional test set, split it. Once we build the model, we'd iterate on it until we got something that predicted correctly. And this particular use case checks off a lot of boxes, because if we can use less electricity to melt steel, that's going to help our CO2 footprint, that's going to help our costs, and it's going to help our throughput. So it's about the perfect traditional machine learning project we could find. This is just a picture. We do have 2 electric arc furnaces. They're very large, 150 tons. It takes over an hour from introducing scrap to being fully melted. So we actually introduce scrap, open it, melt that first. We open up the roof and we add more. So it's 70, 80 minutes tap to tap time. The picture shows, this is the roof of the furnace. The electrodes come in here. It's 3-phase AC current, up to 80,000 amps, 1,000, 1,200 volts. And this is the shell of the furnace down here. The scrap's melting down in this area. And then you can see here, when it's finished, it pours out into a transfer ladle. This goes to the next process for refining, checking the chemistry, and then finally making a slab out of it. The project approach, again, very traditional. All of the discovery phase, EDAs, exploratory data analysis, prep the data, data engineering, and then running through the models, iterating it, checking it. We had to do several things. I'll give you an example. We make austenitic and ferritic about 80-20 split. We have to have 2 different models for those because the targets are a little different, the scrap act's different, that kind of thing. And okay, here's some results of one of the iterations of our model. And you can see on the shaft plot, we've got a lot of features that we had to add into the model, surprisingly enough. If you think about the processes I've described it to you so far, you think, okay, it's so much scrap. Maybe if it's fluffy scrap or dense scrap might make a difference, what type of scrap it is, and maybe the conditions of the equipment a little bit. But in actuality, we had over 20 features listed in the model. And the other thing I noticed when I was putting these slides together was, it's been several years ago, but we had several pair plots that were fairly linear and some that were kind of bimodal and some that were a little bit all over the place. So even in a bound system where you have a lot of data, years and years worth of data, you still have to do a lot of tweaking on something to get it believable to the end users. And then I think this is our final 0.72, but I could be wrong. So good enough to industrialize and give us some benefit. And this is the end result of the model itself. So on these histograms, you can kind of see the orange is before, the blue is after. And this is for austenitic and ferritic heats. So the blue is using the model. We tightened up the curve, and we moved the curve down in both cases. So this results in about 2 to 3% benefit in kilowatt hours put in for each heat, which, a few percent may not seem like much, but this is 50% of our electricity we use at NAS. 50% is used to melt the stainless. The other 50% is to run the rest of the plant. So it's significant. A few percent is measurable. Now, this is not a closed-loop model. What this does is it makes a real-time prediction, updates every 10 to 15 minutes, and it gives the operator on the HMI an indication here of when they should stop the heat, basically. It's saying, okay, this is what I'm predicting, kilowatt hours, you're within 5 minutes, 10 minutes, go check it visually. If there's anything else, they can bypass it, but the idea is to follow it, and of course, we keep metrics on that. I think this is the final slide on this. So this, I just wanted to show you, this is a representation of the first basket we put in, and then there's a pause time. And this is important because this can affect the model. This can affect how much more you have to basically reheat if you had a problem with the roof open or something with the electrodes. So on this is the actual about 24 hours that I grabbed a few weeks ago. So this is the actual kilowatt hours building on each particular heat, and the red line is the prediction, okay? So you can see it kind of follows, and it does update based on current process procedures. So, okay, moving on. I've got 6 minutes, it says, so I'll get through this fairly quickly. This is changing gears completely. This is the first thing we talked about was traditional machine learning. This is more of a generalized signal modeling. This is a use case we used with a company called Falconry. So they have a product in the cloud which does anomaly detection, which I understand is not the end game by the last speaker. But in any case, that's what we're trying to do with this. Why is that? Because we have 30,000 signals. No one can look at it all. And I want to know if something's getting anomalous. Now, we're still in process, and there's some ideas on how we can prioritize that and raise the importance on some of that. But this is univariate modeling, one-by-one signals, 6 to 12 months of data used to train the model. This is an example of the interface. You can see here on the left side is a treed out area. Well, this represents the steel plant. So I'll have a hot mill, melt shop section, and then subnodes. And the idea here is that if you've got some issue on a reheat furnace or one particular part of a machine, you should see anomalies in the vertical region. This represents time. This is 7 days. And each one of these swim lanes is individual tags that I've sent to Falconry to do the machine learning on. There's a scale here. So yellow is terrible. And then blue is like it's acting like it normally should. So normally we focus in on these. If it's yellow, there might be a data issue, something like that. But we're just have this implemented in the last few months and excited about where it's going. I'll show some examples of this. So this is a specific example of basically the air pressure jumping up on a bander machine in our hot mill. And it was very apparent when I looked at the heat map because the heat map shows this up and down like, okay, something's wrong, even though it's yellow. And looking at the real-time trend on active factory, you can see all these bumps in the air pressure on the bander machine. Next two examples are a little bit more, not as dramatic. This one is cooling water flow on one of our sensors in our furnace. So this one, again, this was blue, 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 and then I saw this, and a little bit more, and then major anomaly, and then it went normal again. So these are certainly things that you would not normally see, an operator wouldn't normally see, and can lead to downtime, availability issues. So that's what we're trying to implement. Like I said, this is very raw data. It's kind of looking at the matrix, so you have to get used to looking at the heat maps a little bit. This last example was very small anomaly, but I know that these variables, as a SME, these should not have any anomalies. In this case, we had some gas valves that saturated 100%, so possible calibration problem on zone 2 in our reheat furnace. I've got a few more slides on this that kind of step through the workflow, maybe a little bit better than the ones I showed you so far. So this is very strange, anomalous, like not too much is going on here, but for hydraulic oil, so we want to check it out. When we switch over from anomaly, score, heat map to real time, it still shows this is what it thinks is anomalous in this area. And I can tell right here, this is kind of lower than normal, but some of these little step changes are causing havoc within the model's brain. And then finally, within the same platform, the Falconry platform, you can do these SVD charts. So here you can look at what it normally was for the last couple weeks versus what it was during the anomaly period. So you can actually see the range and maybe if it's acting a little different. So we're excited about this, still in the process of implementing it, as well as many other use cases in-house. One I'll show here in the last few minutes is using vision systems. And so this is not overly sophisticated, but the idea here is we're going to try to use this general Python coding and general industrialization to use in more than one case. In this case, we're looking at this. This is one of our Zenzimer mills, and there's a door on here. And we want to know what the position of this door is. And it's not easy to put a limit switch or LVDT or proc switch or maybe a laser center that's far back. But anyway, we had a camera. So we're going to use this camera, and we're going to try to determine the region of interest, train the model, come up with very high accuracy on what that position is, and then industrialize it. And eventually, we feed this back into our historian. So we're going to feed that back so we can use this for time studies or for alarming or anything like that. So this is kind of the methodology we're looking at in-house to do some vision systems. Aside from that, we've got a picture of an AGV here, nowhere near Caterpillar performance at this time, but this is kind of new, at least within our industry. And then we're looking at augmented reality with glasses. We already have a lot of mobile HMIs, a lot of mobile devices, operations people use to walk around. I already mentioned some of the safety use cases. A lot of it has to do with predictive statistics with our safety database. And we are looking at this. On language processing, there's a lot of talk about it, and I'm not sure where it's going to land. So what we're doing right now is we're capturing all that data. We're capturing all the log files from every 12 hours, from every line, every maintenance log, and we're putting that in the SQL so that we can eventually use that for some machine learning cases. Okay, that's pretty much all I had as far as slides, but I do want to circle back around to the pogo stick. So in my impression is we're still within manufacturing, still got the pogo stick trying to do something, and we're still got connected to it. We're still tethered to it. We're still using machine learning, AI, as maybe an assistant. It maybe as an assistant to the operations people and the SMEs throughout our plant. The good news is it's open for opportunity. Things are changing every couple weeks or every couple months, as you all know, and we look forward to what comes in the future. Thank you.
All right, thank you. We have time for a couple questions. It looks like we go in here.
Thanks. We're seeing a trend with materials providers trying to move up the value chain a little bit. And I'm just wondering if you see any opportunities in things like thinking about demand, price volatility, maybe making custom shapes to serve your customers better, and whether there's any opportunities for you guys there.
Well, for me at least, our effort has been focused the last 4 or 5 years since we started digitalization, really to address problems with either uptime, reliability, quality issues, or anything like that. That being said, there's a lot of case, obviously, for machine learning within logistics. One completely, I didn't even talk about this, but we are working on project for our warehouse, inventory warehouse, specifically consumables. We use a lot of acid, we use a lot of paper, interleaving paper, so a lot of data on that, so we're doing that. As far as end customers and product, I've not had a good feel for that yet, or we're going to change much on that side. But certainly logistics, optimization of process, we're starting to look at.
Thanks for the great presentation. We've heard a few times about the importance of subject matter expertise in industrial AI. As a small team of 6 inside a pretty large organization, I imagine that could be challenging. What have you found has worked best to get subject matter experts' knowledge and get them involved in development?
Well, for sure, if you can help their job, they're going to be on board. So we've been through a few iterations of our digitalization team, and that's another big issue is personnel. Keeping personnel, training personnel, getting the people. So we've turned over a few people, but in the meantime, we've kept some of the people out within the plant, out within the departments that are the actual supervisors, the operations supervisor. The metallurgist in charge of the hot mill is an expert on Python. He can do anything on that SQL or Python. So this is a good ally in the fight we have to implement it throughout the plant. So we just work on that. We, even though we only got 4 or 5 people teams, I've worked in the plant for over 25 years. My supervisor is electrical engineer. He's worked in the melt shop and the hot mill. So we have, basically you have to build relationships with people. You have to build relationships, and if you can help them with a query or one of the UIs, one of the dashboards, even though it doesn't add a huge ROI or anything like that, you get some buy-in. You have to get some buy-in from the team members because we can't do it without them. That project for the EAF, it might be hard to believe, but every operator that's worked there for 30 years probably didn't believe that the machine learning would do better than he did or she did, right? So you have to do a lot of data visualization, prove it out, sit with the people. It's a lot of communication, a lot of hard work. So,
actually, I'm gonna key off that last one because that was gonna be my question with that EAF, because I've got friends who work in Exxon and pipelines. I'm at McDonald's, trying to tell operators when to put more baskets of fries in, and all of us run into this trouble of, no, I've been doing this for 30 years. I know, right? And so that can be a real change management question whenever you do any of these sort of use cases. And just wondering if you have some tips to share with us around, other than just communicate, is there other things that you've been doing to help, through the change management journey, particularly at the operator level?
It's hard, but I think it's turning around. Like with ChatGPT, some of the operators are helping their kids in high school with papers with that. So they know the value of AI, and they honestly, some of them are like, why aren't we doing more here? So I think it's turning around. 5 years ago, it wasn't. My experience has been from the bottom up. So like I said, my team gets involved in the morning meetings, goes out to the control room, sees what they're looking at, talks to the operators, and then talks to their supervisors and tries to have them get on board, the SMEs get on board with what we're trying to do. And also the SMEs drive part of the project. They have to be the data translators. They have to give us what insights to look at on the data engineering, right? So I think from the bottom up is the way to go. That we did talk earlier about buy-in from the top down also, which is good and required. So, I'm not going to go to my boss and say, hey, you need to force this manager to use this model or whatever we built. But, I mean, they ask about it is enough. Enough is their awareness of it and trying to push me and my team to do better. And then we just try to work directly with people. But it is very difficult with so many people. So.
Oh, hello. Thanks for the great talk. It's cool that you're able to detect these anomalies, but then can you talk about the next step? So you see it, how do you do the root cause investigation? And then what's the time lag between you see something, you then diagnose what the real root cause is, and then have a permanent fix? Yeah. That is still our challenge for sure. As far as anomaly detection, okay, within any manufacturing, we've got a lot of PLC high-speed systems, level 1 alarms, right in the operator's face, hey, something's going to break. What I showed you before with the heat maps with Falconry is more of a, that gets updated every hour. So it's not something that's going to tell you something that's going to happen 5 minutes from now. What I've talked to them about and what we're trying to work on is
contextualizing it more, and also kind of giving priority to probably a little bit of supervision as far as which swim lanes or which variables we really are interested in. We're really interested in. So we try to give maybe some additional weighting or something like that. But at the end of the day, someone's got to actually look at it. Someone that knows something has to look at it and act on it. So we're still not there yet on that. Also, the platform itself, I think I showed you, it'll give you some violin charts, and it'll let you do some of the quick analysis on it. So we're kind of working with Falconer to get to a point where it can almost self-diagnose. But right now, there's definitely a lot of noise in there, and it takes SMEs to look at it.
Thank you so much. I can tell a lot of what you've done there is a result of many years of trust. So it's really cool that you were able to accomplish that. One more round of applause.
Thanks.